This is Brian Putt. Today I'd like to talk about reliability models. Evaluating the reliability of products requires considering uncertainty. Simulation using SIPmath can bring clarity to the implication of reliability and enable us to make better decisions on which product, based on its cost and budgeting, for reliable operations. Let us consider an example problem. Let's assume the equipment has a mean time to failure of 250 days, and this will be modeled by an exponential decline distribution. The time to repair is modeled as a triangular distribution with a minimum days of 7, a most likely of 14 days, and a maximum of 40 days. And we're going to consider 7 cycles of the equipment running and then being repaired and running and repairing and so forth and so on. So these two graphics, the one on the left shows the failure time per cycle. So the blue line shows that the average failure time is 217 days. And it's not normal distributed. It's got this tail on it. But when I average the 7 cycles, it starts to look more like a normal distribution in the red line. Similarly, the time to repair per cycle for a single cycle is shown in the blue, with an average time of 20 days. When I average those, we get the red line. So it also has an average time of 20 days. The cost of repair we'll also consider as a triangular distribution with a minimum of $1,000, most likely of $1,500, and a maximum of $3,000. We've shown the distribution chart here on the left, which is not symmetrical, and we've shown the cumulative distribution functions on the right. So what is our opportunity statement following a decision quality process? So the first question is, what is the cost of operation at a discount rate of 8%? And what is the appropriate annual budget to fund the repairs? We might look at some other considerations such as safety, production stoppage, or total expense of repair to include spare parts inventory. But we're not going to do that. We're just going to keep it simple today. So when I put these into a model, I get a number of different outcomes. So shown below are 3 different schedules. These are deterministic schedules. In the first one, we can see that it's a fairly short time to repair. We get through the 7 cycles fairly quickly. On the right, we have long times to repair, and it takes a long time to complete the 7 cycles, and in the middle is somewhere in between. But you can see there are many different outcomes. These are just 3 of 1,000 simulations we're going to use in the analysis. Can we improve the model? Well, the exponential decline is okay for the mean time to failure, but oftentimes as equipment ages, the time to failure decreases. We can reflect this using the Weibull distribution, which has these qualities. The triangular distribution for time to repair is easy for our subject matter experts to assess. They only have to assess a minimum, most likely, and maximum. However, perhaps the Poisson distribution may be more representative in our model. Having reviewed the frame of the opportunity, we now need to move over to the model. We'll review the model's existing distributions. We're going to understand the differences in the Weibull and the Poisson versus the exponential and the triangular. We'll incorporate these distributions in our model. We'll propose a budget solution for the reliability of our machine. See you in part 2 of this video.